All right, so in this video, let me fill in some of the details that I skimmed over before on how to estimate the parameters for a Gaussian distribution based on data. So we're going to do maximum likelihood estimation, and our assumptions are as before. So I have data points x1, x2, xn, so there are n data points. Each of them are d-dimensional, and we assume that they are drawn IID, that they are IID drawn from a Gaussian distribution with mean vector m and covariance matrix C. So the mean vector is a d times 1 column vector by our convention, and the covariance matrix is d cross d, and if the covariance matrices are non-negative definite, let's for simplicity assume that it's positive, strictly positive definite. Assume that C is this is our notation for positive definite, is positive definite, right? And so basically the distribution is characterized by this parameter theta that consists of m and c, and we would and the maximum likelihood estimate of theta is basically the argument of the maximum. So the whatever maximizes the likelihood function, basically what's the joint density of the data I'm seeing, right? And so that is my theta hat ml, which is of course a function of the data. That's sort of the definition of maximum likelihood estimation, of course. And since these are IID draws, we can write them as a product of the marginals, right? So the joint density of is a product of the marginals, and the moment you have that, it makes sense to take a log so that the product becomes a sum. And whether I maximize the original joint density over theta, or whether I maximize the log of the joint density over theta, doesn't matter. The location of the maximum, which is what I want, stays the same. So this is the same as argument of the max over theta of the log of the preceding thing, which of course becomes a sum. I equals 1 to n log of the likelihood of the ith data point. And remember what the Gaussian density is. The Gaussian density p theta of xi, of course, in d dimensions. What is it? It's exponential minus half xi minus the mean covariance inverse. Of course, xi minus mean transpose covariance inverse xi minus the mean, divided by 2 pi to the dimension divided by 2 times the square root of the determinant of the covariance matrix. So the absolute value sign that I have denotes the determinant of C. So this is the determinant of C, right? And so let's take the log to see what that looks like. So log of p theta of xi, what is it? It's minus half that quadratic term that we had in the exponent. Now it comes out here, minus half log, well, minus d over 2 log 2 pi. This does not depend on the parameters m and c at all. Minus half log of the determinant of C, right? That's what P theta of xi, a single xi is. So we want to maximize the sum of these terms over m and theta given my data points xi's. So let me write down the sum. That's the cost function we wish to, or the utility function that we wish to maximize. And I'm going to drop. I'm going to drop this. Drop this since it does not depend on the parameters we wish to estimate, right? So once I drop this, I'm going to get this cost function or utility function j of theta, which is the sum of these guys. So what is that? Minus half times the sum I equals 1 to n xi minus m transpose C inverse xi minus m minus, and now I have this term that is being added up capital N times for the n data point. So minus capital N over 2 log of the determinant of C. And we want to maximize this j of theta over theta, which is of course m and c, right? So at this point, it becomes interesting to introduce the precision matrix again. So because the precision matrix P is defined to be the inverse of the covariance matrix, and if you define it this way, the cost function looks, or utility function looks a little nicer, and it will be easier to optimize this over m and p. Remember, we are trying to maximize this function with the data points being fixed, and I'm trying to maximize this function over m and c. Anything that is a one-to-one relationship between m and c and any other parameterization, the location of the maximum will remain unchanged, right? Essentially under that transformation. So whether I maximize over m and c or m and p does not matter. I can just go back and forth between these parameterizations. So that's an important thing to note. So with this change of parameterization, how do I write that? Remember that the determinant of P is of course 1 over the determinant of C, and we assume that both of them are positive. So it's all good. These things are just positive numbers. So once I plug those in terms of P, the j of theta becomes minus half summation I equals 1 to n xi minus m transpose P. And that's much nicer than C inverse, right, in terms of maximization, minus n over 2. And now it's not minus anymore, log of, I have log of the determinant of P, and so I'll have plus log of the determinant of P. And we want to maximize over m and p to get the maximum likelihood estimate, right? And so, well, this becomes an interesting exercise in just sort of computing first derivatives and setting them to 0. Why? Because these are very nice functions of m and p. So let me point this out. As a function of m, as a function of m, j of theta is quadratic, right? you have x minus m transpose. Remember, x is just a constant now. It's just data that is given to us. So m transpose and then x minus m again with a matrix in the middle. So it's a quadratic function of m. And let's look at how many, what's the sign of the leading term of the quadratic. There's a minus sign here in front of this m. There's a minus sign here, and there's an outside minus sign. So there's an overall, 3 minuses becomes a minus. So the term involving m transpose m is has a negative coefficient. So if you note that a quadratic, imagine that this were just a scalar. If you had sort of minus m squared plus bm plus c, this kind of function, that looks like this. So this is sort of concave, and sort of the global max can be found by setting the derivative to 0. So, in the case of vector m, all I need to do is set the gradient to 0. It's a quadratic in m with a which is concave, and I'm going to just compute del m by j theta and set it equal to 0 at m equals m hat maximum likelihood, right? That's basically the idea. So let's just take one of these terms that we have and take the gradient for that. So a typical term is, let me change pen colors again, minus half xi minus m transpose p xi minus m. I have this term and I take the gradient of this term. Well, so I have the minus half factoring out. And when I have xi minus m transpose something, I'll just get, and I take the gradient with respect to m of this term, I'll get just a negative sign. So I'll have a minus sign there times p times xi minus m. So that's when I differentiate with this term with respect to m while keeping this, this other term, while not touching this other term. And then when I do the same thing for this term, I'll get exactly the same thing again. So I'll have a factor of 2 here for the two terms. And if you work out, there's a minus here, goes away, 2 and 2 go away. So this guy is just p times xi minus m. So when I put all those terms together, remember there's a sum of n of those terms, then I'll just get a summation like that. And of course, this term does not depend on m at all. So the gradient with respect to m of j of theta is summation I equals 1 to n p xi minus m, and I'm going to set it equal to 0, right? For at m equals m hat ml. And now we have assumed that p is positive definite, so I can multiply both sides by the inverse of p. So multiply by p inverse on both sides. So the p goes away on the left hand side, and of course p inverse times 0 is 0. So basically I get summation I equals 1 to n xi minus m is equal to 0, which means that summation I equals 1 to n xi is equal to n times m, which gives me what I had before, that m was just the empirical mean of the data vectors, that the m hat ml is just the empirical mean of the data vectors, right? So that's a simple exercise in gradient computation, and we get the answer that we had gotten before, just we did it a bit more slowly. Okay, so now the more interesting part and more challenging part is to understand what this is like as a function of P, the precision matrix P. So so what does the utility function j of theta look like as a function of P? So let's look at the term log of the determinant of P. This is something I'm not going to show, but we're going to assume that this, I'm going to assert that this is concave in P. That is to say, in the high dimensional space of positive definite matrices, it looks like this. The proof is actually not that bad. It relies on proof. One possible proof relies on the sort of spectral decomposition of positive definite matrices, which give me non-negative or positive eigenvalues, and the concavity of the scalar log, concavity of log of x, where of course we are interested in the regime of x being positive. So we'll just assume this, right? So once we assume this and go back to the cost function, what do we have? We have a term that is concave in P and a term that is linear in P. That's why that substitution of C inverse equals P is so nice. So a linear function is both convex and concave. So the overall sum of these two functions is concave, which means that, again, I can find the global optimum by setting the gradient to 0. So basically, let me state this. So j of theta is concave in P, which means can find P hat ML by setting gradient of this with respect to P to 0. Now, how do I define the gradient with respect to a matrix? Exactly as you would expect. The gradient with respect to a vector basically is a partial derivative with respect to the components of the vector. It's that vector of partial derivatives. Here, I'm just going to take partial derivatives with respect to each entry of the matrix, and the gradient would be the matrix of these partial derivatives. So let me just specify what I mean in more detail. So basically, what I'm saying is that this guy is remember, I mean, working in d-dimensional space, so this P matrix is d by d. So is a d cross d matrix with I jth entry, exactly what you would assume. So basically, the partial derivative of that utility function with respect to the ijth entry of P. So that's how I define it. And so by setting this gradient to 0 just means that the partial derivatives of the cost function or utility function with respect to each of the entries of the matrix is 0 at the ML estimate of P. That's basically what we are saying. Okay, so now we have to compute this, right? So let's look at the terms that we have here in the cost function. So we have a term, basically xi minus m, well, we're going to fixing m and optimizing over p, and x's of course are fixed. So I have some constant vector xi minus m transpose multiplying p, and then again xi minus m. So I have a typical term like a vector transpose times p times the vector, right? So I need to take the gradient of that kind of term, and then I have to take the gradient of this log of the determinant of p, right? Those are two components I need to compute the gradient of the utility function with respect to p. So let's go back and do that. So let's consider, I have two building blocks, right? So what is the gradient of something like a vector times p times a, right? That's the vector a is fixed with respect to p, it doesn't vary, and I'm trying to take the gradient of this guy. So let me write down what a transpose p a is. Just write it down. So that's what summation I equals 1 to d, summation j equals 1 to d, ai pij aj. That's all it is, right? It's a scalar that is that comprises all these terms, right? So del a transpose pa del pij is just whatever that ijth term is. So that's ai times aj. And so that's basically my ijth entry of the gradient. But what is ai aj? That is just the ijth entry of the outer product of a with itself. There's other slick ways in which I could have derived it by introducing trace and all that, but this direct approach is absolutely fine for our thing. So what we have just shown is that the ijth entry of the gradient is the ijth entry of the outer product. So what we have just shown is that the gradient of a transpose pa is simply the outer product a transpose, and you can see that this is, d cross 1, its transpose is 1 cross d, so it is indeed a d cross d matrix, this outer product matrix, right? That's what it is. Okay, so that's one thing that I need. Then I need the gradient of log of the determinant of p. This is of course a little more tricky. So I'm going to first use the chain rule. The log of the determinant of p with respect to the determinant of p is just, log of x, the derivative of log of x is just 1 over x. So I use the chain rule and I get 1 over the determinant of p times the gradient of the determinant of p with respect to p. So now I need to get very specific about, well, some form of determinant where I can compute this derivative with respect to an arbitrary entry of p. So what I want is to be able to compute the partial derivative of the determinant of p with respect to some arbitrary ijth element of p. Now we know actually how to compute determinants. So we typically compute it using so-called minors. We basically delete the ijth rows and compute the determinant of a smaller matrix, etc., etc. So we actually have to go into that level of detail. So let's do that. So let's say I am computing determinant, and let me just write down the expression as I talk. So basically, the determinant of p is one way to do it is to I look at the the jth column, expand it along there, and say let me look at the the ith row there. So the entry is pij. I'll delete the ith row and the jth column and get a matrix, a smaller matrix, and take the determinant of that. That is the so-called minor. And that's why I'm going to denote it as mij. And I will also have to multiply it by -1 to the I plus j. So basically there's alternating sign business happening as I proceed along either a row or a column. And that is one way to compute determinant. In fact, we sometimes in elementary linear algebra courses, we define determinant that way, actually, right? So this is how we compute determinant. So what is, let me just remind you what this guy is. This is a minor, so which is the determinant of the matrix obtained by deleting, by deleting row I and column j of P. So that's the determinant of, that's one way to compute the determinant of matrix. And note that the entries, so note that Mij does not depend on the entries of P in row I and column j by definition, because I have deleted those rows and columns and then computed the definition. So the determinant, which means, of course, it it's a constant with respect to Pi, with respect to the del by del Pij. It just pulls out of the constant when I take the partial derivative with respect to Pij. So now that I know that, it's easy for me to compute the partial derivative of P with respect to Pij. It's just -1 to the I plus j Mij. It's the only place where Pij appears. Everything else is independent of Pij, as it turns out. Because in all of the terms here, row I has been deleted when computing those minors, which means once row I has been deleted, these minors do not depend on any entry in row I, including the entry that I'm differentiating with respect to Pij. So that's how I get that. All the other guys just die out. Pik for k not equal to j, those those have derivative 0 with respect to this, partial derivative 0 with respect to this particular element, right? So what we have shown then is, so this is the ijth entry of the gradient of the determinant of P with respect to P. So this is del P of P, the ijth entry, ij is -1 to the I. I'm just rewriting exactly the same thing, right? Okay, fine. Now let's go back to what we are interested in. That was this guy, the gradient of the log of the determinant of this, right? So let's copy that here below. And now plug in what I have there. So the ijth entry of this del P of log of P, the ijth entry of this is 1 over the determinant of P times -1 to the I plus j Mij. And now, hopefully, you are remembering how we compute the inverse of a matrix. How do we do it? One possible way to do it is exactly this. You basically compute the minors, multiply by these things, divide by the determinant, and then you transpose the thing. So what this guy is actually P inverse, but the jith term of P inverse. This is again, you can go back and look at your basic linear algebra texts, and you'll see how inverses are computed, and this is how it's done. Actually, one of the key ways in which inverses are done. I mean, there are many ways of doing it, of course, but this is one of the ways that is very, very commonly taught up front. So what we have just shown then is that del P of log of the determinant of P is P inverse transpose, which is of course the covariance matrix transpose, which is the covariance matrix is of course a positive definite symmetric matrix. So it's just the covariance matrix or the inverse of the precision matrix, right? So now we are ready to, so we've got two facts. You have this guy, and let me just write down the other thing. You remember we had shown that del P of A transpose PA is AA transpose, the outer product. So these are the two things that we need. And we go back to the cost function that we had. I have to scroll up quite a bit. Keep scrolling. And we are back here in this cost function. Let me just copy that. So once I copy that and apply these things, what do I get? So del P of J is minus half. I have this sum of these terms, and each term, the gradient is xi minus m xi minus m transpose. That's my AA transpose business coming in here. I have that plus n over 2 times the gradient of the log det of P, which is just the covariance matrix actually, right? And this is equal to 0 for whether I call it P equals P hat ml or C equals C hat ml, it's the same thing. And so when I take it over to the other side, I get that C hat ml times n is equal to that sum of the outer products. So the factors of 2 cancel out, and basically I get what I had before. I had stated more quickly before that it's simply the average outer products. And of course, remember, we are plugging in the, I'm jointly optimizing over M and C. So the M that goes in here is the M you got from the ML thing, right? So basically, I basically have this concavity over M and P, and I set the derivatives to 0, solved it, and I got M hat and C hat, and C hat is just the empirical average of these outer products that I get from when I sort of subtract out M hat from the data points, right? So and that's the end of the derivation of the maximum likelihood estimates of the parameters of a Gaussian, and these of course are the building blocks for using the EM algorithm for estimating the parameters for a Gaussian mixture.